Hi there, this is Steve Earth. This is my final project presentation for the Computer Vision class. I'm just going to try to breeze this really fast because so far all my practice ones have gone like way over time. So my project was on spherical transformations, about how to take an image of a sphere and preserving the sphericality and move it onto another sphere. It's somewhat similar to homework 2 where we were preserving planarity, though for there you needed 4 points in the image and 4 points in the post image that were all coplanar, but we don't need anything like that this time. And then the idea is to take the what we did before with the panorama where we put it on cylindrical coordinates. Here I'm going to be doing everything in spherical coordinates and stitching things together. So I'm going to zip through this. Originally I was going to do an Earth, but then decided to actually do it with my own pictures. But we're going to, part of the input is it's going to take a arbitrary axis and spin it around that axis. So I'm going to go through this really fast. First, the steps are to first find the spheres. I use something called a Hopf transform. So the details, I can go into more details in the paper, but essentially you look at the edges. You find the edges first using, say, the canny method, and then every point looks at all possible circles and radii it might be a part of, and they vote for the one that's most common. Then I computed a rotation matrix, and this was, for me, the most interesting part mathematically, but I don't have enough time to go through it in detail, but suffice to say, this is what you get in the end. Then for each pixel that's in the image, I check to see whether it's in the ball or not. If it's not in the ball, I just leave it alone. If it is in the ball, there's some tricky stuff you have to do. So unfortunately, it's not quite as simple as just multiplying by that rotation matrix that I came up with. Because first of all, you have to do some translation, which I made a mistake originally and forgot to translate things back. The other thing is that you've got these multiple images going on. So it turns out the way I imagine it is the camera's looking down the z-axis, and so if it's less than 0, you got to switch to the image of the back. So I think this one picture sort of describes the intricacies you have to be careful of, because not only are the circles potentially different sizes in different places, depending on the vantage point of the camera, you also have right and left reversed. All right, there is a similar issue with the bilateral, or the bilinear interpolation. There's a misspelling on the slide. So basically, you have to make sure that when you look at the quote-unquote adjacent pixels, if you're on the boundary, you have to wrap around to a different image. I basically looped through that a bunch of times. It was taking a long time in text, but eventually got it done. So let's take a look at the results. All right, so here's my first video. It's a cue ball spinning around furiously. Okay, sorry, my brother made me tell that joke. All right, so here's the real thing. So I took a little rubber ball. It was colored, and I took a picture of the front, and I took a picture of the back. And let's take a look at the videos. So I don't really have time to show all of them, so first I'll just show this one here. So notice it just looks like a normal rotation, spinning around, nothing too exciting. That's because I'm rotating around the z-axis. So now I'm going to rotate around the y-axis, and then the x-axis, and then around an arbitrary axis. So I think I actually picked a point about right here, and that's what I put in for the input, and it went ahead and spins it around. So for future work, one thing I'd like to do is to try to speed it up, maybe by threading or something, so it could actually work in real time. And then once we get it in real time, I'd like the input to be, instead of buying a command line argument, to be like a click of the mouse. I'd also like to get rid of some of the light effects that were going on. And I think we could prevent that sort of seam that was going on by doing a seam insertion and make it a little bit less jarring. All right, we're right at 4 minutes, so that's it. Bye-bye.